You're listening to the Bare Metal Cyber Prepcast, created to help you succeed in your educational journey. Learn more at baremetalcyber.com, where additional prepcasts, books, and training materials await. Let's get started. Artificial neural networks draw their original inspiration from biology, specifically the structure and function of neurons in the human brain. Biological neurons receive input signals through dendrites, process them in the cell body, and pass outputs along axons to other neurons. These interactions create massive, interconnected networks that enable perception, memory, and thought. Early AI researchers wondered whether such biological processes could be mimicked computationally. They simplified the idea into models where artificial neurons receive numeric inputs, transform them, and produce outputs that influence other neurons. While far less complex than real brains, this analogy provided the foundation for algorithms capable of learning from examples. The biological inspiration is not meant to replicate every detail of neural functioning, but to capture the idea of distributed, layered processing. By studying how brains transform sensory signals into cognition, researchers discovered a metaphor powerful enough to drive modern AI. The perceptron, introduced in the late 1950s, was the earliest model of an artificial neural network. Designed by Frank Rosenblatt, the perceptron sought to classify inputs into categories by applying weights to each input and summing them, followed by a simple decision threshold. For instance, a perceptron could be trained to distinguish between shapes based on features such as line orientation or pixel values. If the weighted sum exceeded a threshold, the perceptron classified the input into one category, otherwise it chose another. The perceptron demonstrated that machines could learn from data by adjusting weights during training, making it an early milestone in AI. However, it was limited to solving linearly separable problems, meaning it could not handle complex patterns such as the XOR problem. This limitation stalled progress for decades, but also planted the seed for deeper models that would overcome these constraints. Artificial neurons, the building blocks of neural networks, operate by processing inputs through weights and applying transformations to produce outputs. Each input is multiplied by a weight that reflects its importance, and all weighted inputs are summed. A bias term may be added to shift the output, giving the model flexibility. This sum is then passed through an activation function, which introduces nonlinearity. The output becomes the signal for the next layer of neurons. Conceptually, this is like evaluating multiple factors, each weighted differently, before making a decision. For example, when assessing whether an email is spam, one weight might amplify the presence of certain keywords, while another might discount the sender's reputation. By adjusting these weights through training, artificial neurons collectively form networks that capture intricate patterns in data. Activation functions are critical to making neural networks more than just calculators of weighted sums. Without them, networks would be restricted to linear transformations, unable to model complex relationships. Functions like the sigmoid compress outputs into ranges between 0 and 1, useful for probabilistic interpretations. The hyperbolic tangent, or tan, scales outputs between -1 and 1, providing centered values for smoother optimization. The rectified linear unit, or ReLU, became especially influential, allowing networks to learn efficiently by outputting 0 for negative inputs and passing positive values unchanged. These non-linear activation functions give networks expressive power, enabling them to approximate virtually any function with enough layers and data. Choosing the right activation function shapes learning dynamics, influencing speed, stability, and accuracy. Their importance cannot be overstated, as they are the mechanisms that make deep networks possible. Layers are the organizational structure of neural networks, arranged into input, hidden, and output layers. The input layer receives raw data, such as pixels from an image or words from a sentence. Hidden layers, which may consist of many interconnected neurons, transform the input step by step, extracting progressively abstract features. Finally, the output layer produces the system's prediction, such as identifying an object in an image or translating a sentence. This layered architecture enables hierarchical learning, where each stage builds upon the last. For instance, in a vision task, early layers may detect edges, middle layers shapes, and deeper layers entire objects. The concept of layers illustrates how neural networks decompose complexity into manageable steps, much like humans process information in stages. By stacking layers, neural networks become powerful approximators of real-world phenomena. Single-layer networks represent the simplest form of neural networks. They consist of an input layer connected directly to an output layer without any hidden layers. Such networks can perform basic classification tasks, especially when categories are linearly separable. For example, a single-layer network might distinguish between two types of objects based on straightforward features like size or brightness. However, these networks cannot capture more complex patterns requiring nonlinear relationships. Their limitations became clear in the 1960s, leading some researchers to question the future of neural networks. Despite this, single-layer networks remain useful as building blocks and for illustrating foundational concepts. They serve as an entry point for understanding how neurons combine, and they laid the groundwork for the development of more sophisticated multi-layer models capable of handling intricate real-world problems. Multi-layer networks extend beyond the limitations of single layers by introducing one or more hidden layers between inputs and outputs. These additional layers allow the network to learn hierarchical patterns representing increasingly abstract concepts. For instance, in natural language tasks, early layers may capture word associations, while deeper layers learn sentence structures or semantic meaning. The presence of multiple layers enables networks to model nonlinear relationships, solving problems like the XOR function that single-layer perceptrons cannot handle. Multi-layer networks demonstrated that complexity in representation arises from depth as much as from breadth. They paved the way for deep learning, where dozens or even hundreds of layers work together. For learners, multi-layer networks illustrate how scaling architecture in depth unlocks capabilities once thought unattainable in AI. Backpropagation is the learning algorithm that made training multi-layer networks practical. It works by comparing the network's predictions to the correct answers, calculating the error, and then distributing that error backward through the layers to adjust the weights. The process relies on gradients mathematical measures of how much each weight contributes to the error. By iteratively updating weights to reduce error, the network gradually improves its performance. Backpropagation addressed the challenge of training deeper networks, enabling learning across multiple layers instead of only at the output. The algorithm became a cornerstone of modern neural networks, proving that complex, layered systems could be trained efficiently. It is often described as the mechanism that unlocked the power of deep learning, transforming neural networks from theoretical constructs into practical tools. Gradient descent is the optimization method that underpins backpropagation, guiding weight adjustments during training. Imagine standing on a hilly landscape in fog, trying to reach the lowest valley. You cannot see the entire terrain, but you can feel the slope beneath your feet and step downward. In neural networks, the landscape is the error surface, and gradients indicate the direction of steepest descent. By taking small, iterative steps in this direction, gradient descent gradually minimizes error. Variants such as stochastic gradient descent introduce randomness, using subsets of data to speed learning, while adaptive methods like ADAM adjust step sizes dynamically. Gradient descent embodies the principle of incremental improvement, ensuring that networks converge toward optimal configurations. It is a practical and elegant solution to the immense challenge of training large systems with countless parameters. Loss functions provide the metrics that guide gradient descent by quantifying how far predictions are from correct answers. Different tasks require different loss functions. For regression problems, mean squared error measures the average difference between predicted and actual values, penalizing large deviations more heavily. For classification, cross-entropy loss compares predicted probabilities with true labels, rewarding accurate confidence while penalizing misplaced certainty. The choice of loss function shapes the network's learning trajectory, aligning optimization with the ultimate goals of the task. In essence, the loss function provides feedback on performance, defining what it means to be better or worse. By formalizing error, loss functions transform abstract tasks into measurable objectives, enabling systematic improvement through training. Training epochs describe how networks learn by repeatedly passing through the dataset. Each epoch represents one complete cycle where all examples are processed, predictions are compared to true outputs, and weights are updated. Multiple epochs allow the network to refine its internal representations, gradually improving accuracy. Too few epochs may leave learning incomplete, while too many risk overfitting. Monitoring performance during training helps determine the right balance. The idea of epochs mirrors human learning. Repeated exposure reinforces patterns until they are ingrained. In neural networks, each pass deepens the system's grasp of patterns, moving it from rough approximations toward refined predictions. Understanding epochs highlights the iterative nature of learning, where improvement comes from repeated cycles of practice and adjustment. Overfitting is a persistent challenge in neural networks, especially as models become more complex. When a network memorizes training data instead of learning general patterns, it performs poorly on new examples. Overfitting often arises when models have too many parameters relative to the size of the dataset. For example, a network might recognize training images perfectly, but fail to generalize to slightly different ones. This issue underscores the need for balance. A model should be complex enough to capture important patterns but not so complex that it captures noise. Overfitting reveals that learning is not merely about accuracy during training, but about adaptability to future situations. Preventing it is a core concern in neural network design. Regularization techniques were developed to address overfitting by encouraging networks to learn more generalizable patterns. Dropout, for instance, randomly disables a fraction of neurons during training, preventing the network from relying too heavily on specific pathways. Weight decay penalizes large weights, discouraging overly complex models that memorize details instead of generalizing. Early stopping monitors performance on validation data and halts training when improvement stalls, avoiding overfitting from excessive epochs. These strategies act like safeguards, ensuring that networks remain adaptable. For learners, regularization illustrates how careful design choices can balance power with restraint, making models more reliable in real-world applications where conditions always vary from training data. Neural networks are computationally demanding because of their sheer size and complexity. Training requires calculating outputs, errors, and weight updates for potentially millions or billions of parameters across multiple layers. Large datasets compound this demand, requiring repeated passes through massive amounts of information. These requirements stretch memory, processing power, and time. For example, training modern image recognition models can take days or weeks even on powerful hardware. This computational burden has driven innovations in both software frameworks and hardware acceleration. Understanding the heavy demands of neural networks helps learners appreciate why infrastructure beyond algorithms alone is crucial to the success of deep learning. Graphics processing units, or GPUs, have played a transformative role in meeting these computational demands. Originally designed for rendering graphics, GPUs excel at parallel processing, handling thousands of simple operations simultaneously. Neural network training, which requires repetitive calculations across large matrices, aligns perfectly with GPU architecture. As a result, GPUs can train networks orders of magnitude faster than traditional central processing units. The adoption of GPUs revolutionized AI research, enabling the deep learning boom of the last decade. Today, specialized hardware like tensor processing units further accelerates training. The reliance on GPUs illustrates how breakthroughs in AI depend not only on algorithms, but also on advances in computing technology that make large-scale learning feasible. For more cyber-related content and books, please check out cyberauthor.me. Also, there are other prepcasts on cybersecurity and more at baremetalcyber.com. Deep neural networks, often abbreviated as DNNs, expand the basic multi-layer architecture into systems with many hidden layers. The depth allows them to learn hierarchical representations, where each layer captures progressively more abstract features. In image analysis, for example, the first layer might detect edges, the next might assemble those into shapes, and deeper layers might recognize entire objects like faces or cars. This layered abstraction enables networks to tackle problems that were once considered beyond the reach of AI. The success of deep networks lies not only in their complexity but also in their scalability. Given enough data and computing power, they can approximate intricate relationships in ways that shallow models cannot. Deep neural networks thus represent a major leap forward, transforming neural networks from niche tools into the backbone of modern artificial intelligence. Convolutional neural networks, or CNNs, are a specialized form of deep learning designed for processing visual data. They employ convolutional layers that apply filters, or kernels, across an image to detect features such as edges, textures, and shapes. Pooling layers then reduce dimensionality, making the network more efficient while preserving important patterns. This structure allows CNNs to capture spatial hierarchies in images, recognizing that pixels near each other often share meaningful relationships. CNNs have revolutionized computer vision, enabling applications like object detection, facial recognition, and autonomous vehicle navigation. Their design illustrates how tailoring architectures to data characteristics, such as spatial structure, dramatically enhances performance. For learners, CNNs provide a clear example of how specialized neural networks excel when aligned with the nature of their input data. Recurrent neural networks, or RNNs, were developed to handle sequential data where order matters. Unlike feed-forward networks that process inputs independently, RNNs incorporate feedback loops, allowing information from previous steps to influence current processing. This makes them well-suited for language modeling, speech recognition, and time series prediction, where context unfolds over sequences. For example, in a sentence, the meaning of a word often depends on the words before it. RNNs capture these dependencies, giving them the ability to model temporal dynamics. However, they suffer from challenges such as vanishing or exploding gradients, limiting their ability to remember long-term dependencies. Despite these issues, RNNs marked a significant advance, showing how neural architectures could extend beyond static data into the realm of sequences. Long short-term memory networks, or LSTMs, were introduced to overcome the shortcomings of traditional RNNs. LSTMs incorporate specialized gating mechanisms that regulate the flow of information, allowing them to retain relevant context over long sequences. This makes them highly effective at tasks like speech recognition, machine translation, and handwriting generation. For instance, an LSTM can remember the subject of a long sentence to ensure verb agreement at the end. By preserving and discarding information selectively, LSTMs manage long-term dependencies more effectively than simple RNNs. They became a cornerstone of sequence modeling before the rise of transformer architectures, bridging the gap between short-term memory models and the complex demands of natural language and time series tasks. Transformer networks represent a paradigm shift in sequence processing. Introduced with the principle "attention is all you need," transformers replaced recurrence with attention mechanisms that allow models to weigh the importance of each part of the input relative to others. This enables parallel processing of sequences, dramatically improving efficiency and scalability. Transformers have become the foundation for modern natural language processing, powering models like BERT and GPT. Their ability to capture global dependencies makes them effective not only for text, but also for applications in vision and multimodal learning. The rise of transformers demonstrates how rethinking architectural design can revolutionize entire subfields. For learners, they represent both the current state of the art and a window into the future of AI. Image recognition showcases one of the most impactful applications of neural networks. CNNs have enabled machines to detect objects, classify images, and even describe scenes with impressive accuracy. Applications range from photo tagging in social media to medical imaging that identifies tumors. The power of neural networks lies in their ability to learn features directly from raw pixels, bypassing the need for handcrafted rules. This has democratized vision applications across industries, where accurate interpretation of images is critical. For learners, image recognition illustrates how abstract mathematical structures, layers of neurons, and filters translate into tangible capabilities that shape everyday technology. Speech recognition provides another transformative application of neural networks. By converting sound waves into sequences of features, neural models can map audio signals to words with increasing accuracy. Early systems relied on statistical models, but deep learning has enabled dramatic improvements, making virtual assistants and real-time transcription widely accessible. Neural networks can adapt to different accents, noise levels, and speaking styles, illustrating their flexibility. For instance, deep recurrent and transformer-based models now power dictation tools and live captioning systems. Speech recognition underscores how neural networks can bridge the gap between raw sensory data and meaningful human communication, bringing machines closer to natural interaction. Natural language processing is perhaps the most visible arena for neural networks today. From machine translation to text summarization and conversational AI, neural architectures have transformed how machines interact with language. Embedding layers capture semantic meaning, while deep structures handle syntax and context. Transformer-based models, in particular, have enabled applications that generate coherent essays, answer complex questions, and sustain realistic conversations. These achievements show the potential of neural networks to engage with one of humanity's most defining traits: language. For learners, NLP applications highlight how theory and architecture translate into practical systems that reshape communication, education, and knowledge sharing. Healthcare illustrates how neural networks extend beyond consumer tools into life-critical domains. Convolutional networks analyze medical images to detect cancers or heart conditions. Recurrent and transformer models process patient histories to predict disease risks or recommend treatments. Neural networks also assist in drug discovery, sifting through vast molecular datasets to identify promising candidates. These applications demonstrate how AI augments medical expertise, offering support in diagnosis, monitoring, and research. Yet they also highlight the need for rigorous validation, as errors in healthcare carry serious consequences. The intersection of AI and medicine underscores both the promise and responsibility of neural networks in society. Training deep networks presents significant challenges. As layers deepen, gradients used for learning can either vanish, becoming too small to update weights effectively, or explode, causing instability. These issues make optimization difficult, requiring careful initialization, normalization, and advanced techniques like gradient clipping. Hyperparameter tuning, choosing learning rates, architectures, and batch sizes adds further complexity. Training also demands massive data and compute resources, making it costly and time-consuming. These challenges remind learners that while deep networks are powerful, they are not easy to train. Progress depends not only on new architectures, but also on advances in optimization techniques that make learning stable and efficient. Interpretability is one of the most pressing issues with deep neural networks. Unlike rule-based systems, where reasoning steps are transparent, deep networks often function as black boxes. Their decisions emerge from complex interactions among millions of parameters, making it difficult to explain why a model reached a particular conclusion. This opacity is problematic in high-stakes domains like finance, healthcare, and law, where accountability matters. Efforts in explainable AI aim to open these black boxes by developing methods to visualize and interpret model behavior. For learners, the interpretability challenge highlights the tension between performance and transparency, a trade-off central to the responsible use of AI. Ethical considerations in neural networks arise from their widespread impact and potential for harm. Bias in training data can lead to discriminatory outcomes, as seen in hiring algorithms or facial recognition systems. The massive energy consumption of training large models raises concerns about environmental sustainability. Accountability is another challenge. When a neural network makes a harmful decision, who is responsible? These issues show that technical progress must be accompanied by ethical reflection. Neural networks are not neutral tools. Their design and deployment carry values and consequences. Addressing ethics is essential to ensure that these systems benefit society fairly and sustainably. Advances in hardware and software have been essential to the growth of neural networks. Specialized chips like tensor processing units accelerate computations, while software frameworks such as TensorFlow and PyTorch streamline model building. These tools have lowered barriers to entry, enabling students, researchers, and businesses to experiment and innovate. Hardware advances make training enormous models feasible, while software ecosystems foster collaboration and reproducibility. Together, they have created a thriving infrastructure that supports rapid progress. For learners, this illustrates how breakthroughs in AI depend not only on algorithms but also on the ecosystems of tools that enable experimentation and scaling. Neural networks have become the backbone of modern AI, powering advances in vision, speech, language, and beyond. Their ability to learn complex patterns directly from data has made them indispensable, driving progress across industries and research. What began as biologically inspired models of simple neurons has evolved into deep architectures with billions of parameters, capable of feats once considered science fiction. Neural networks are no longer just one branch of AI, they are its defining engine. Their influence is seen in everyday applications and cutting-edge breakthroughs alike, shaping the trajectory of the entire field. Looking forward, neural networks are expected to evolve in efficiency, interpretability, and integration with other approaches. Research is exploring neurosymbolic systems that combine the flexibility of neural methods with the transparency of symbolic reasoning. Energy-efficient architectures aim to reduce environmental costs, while new training techniques promise faster, more robust learning. The future may also see greater emphasis on smaller, specialized models that deliver strong performance without massive computational demands. For learners, these directions highlight that neural networks remain a dynamic field, where innovation continues to redefine what machines can achieve. Their evolution will shape the next generation of AI systems, influencing both technology and society. Thanks for tuning in to the Bare Metal Cyber Prepcast, your trusted source for cybersecurity news and insights. Remember to subscribe at baremetalcyber.com so you never miss an update. And visit cyberauthor.me for best-selling cybersecurity books that equip you with expert knowledge. Until next time, stay secure and stay vigilant.